Good morning, good afternoon. Welcome to this IPCOS webinar on how digitalization can move you forward on the road to net zero. My name is Edwin Wieting. I'll be your host for today's webinar. We have about 1 hour, and in the first 45 minutes or so, Maarten Willems will be sharing his insights and practical experience on digitalization projects in the context of net zero. There's quite a large attendance today with a good mix of people that we've worked with it before, and also plenty of people that we haven't worked with yet. So I'll start with a very brief 2-slide introduction of IPCOS before we get into the meat of the presentation. IPCOS is a company that's been around for more than 25 years. We have about 70-80 people in different locations around the globe. We're a technology independent services provider, and we bring together deep domain knowledge, technology know-how, and experience in IT and OT infrastructure. That combination is really what makes us special. We have an in-depth understanding of process technology and business processes. And with that experience and knowledge, we're able to translate business needs, whether that's at control room level or management level, into digitalization solutions that really empower each member of the organization. We've been lucky enough to work with a broad range of small and big companies in the oil and gas, refining, petrochem, chemicals, bulk chemicals and fine chemicals and power industries. I think on the previous slide you saw some logos there of a few of our customers. That's just a small subset. As I mentioned, we translate business and operational needs into digital solutions that really work. And we do that throughout the customer organization. At the control room level, we help the operations team, for instance, by implementing advanced process control or digitizing the shift logs or automating the daily reporting. For the production engineer and the process engineers, we implement solutions like OEE tracking, performance dashboards, predictive modeling and simulation. And for managers, we provide real-time reporting and dashboards with drill-down capabilities, asset benchmarking, all those type of solutions. And we do this all in reality, not as slideware. For each of the solutions that I mentioned and many more, we have examples of how this was implemented in real life with real results. And some of these examples, I'm sure you'll see passing by in Maarten's talk today. All right, that's it for sales talk today. Let me now introduce the speaker, Maarten Willems. Maarten graduated with a master's degree in chemical engineering. He's worked for 10 years in the area of industrial digitalization. His experience covers real-time monitoring and optimization, data integration technologies, and design of engineering workflows. And over his career, he's had numerous roles working for companies like ADNOC, Arkema, Shell, Rome, Total Energies, and many others. Maarten is currently a project manager in the digital assets team of IPCOS, where he's responsible for project delivery and business development. The floor is yours, Maarten.
All right. Thanks, Edwin, for the introduction. Hope the audio is good, but if I don't hear anything, I'll assume so. So also for me, welcome everyone, and on this webinar about the intertwine between digitalization and net zero. We'll jump right in. So for the outline, you can see that I will be discussing 3 main use cases. I'll start about measuring your emissions, then I'll go a bit more. So yeah, measuring your emissions is all about knowing the total amount of emissions that you produce. Then I'll focus a bit more on how do we identify the main contributors. So where in your process are these emissions coming from? And at the end, there will be a part on reducing these emissions, which of course is the most interesting part. Now, it's a very hot topic, I would say. A few weeks back, we were at a conference in Berlin, Manuchem, and I think around 80% of the presentations there were all about net zero and emissions. All had a bit of a different view on this topic, but it actually shows that it is quite a hot topic, I would say. So I wanted to start a bit with why is that? So we know that the EU wants to be climate neutral by 2050. And the EU has put several measures or processes in place to actually achieve that. Now, the most known is the emission trading system, which is a traditional cap and trade system, which actually creates a market for CO2 emissions within Europe. This system does not cover all the greenhouse gases of Europe. It really focuses on heavy energy using industries and aviation. And so in total, that comes to around 45% of the greenhouse gases in Europe are covered by this system. Now, how does the system work? Every year, there is a certain amount of emission rights that is made available by Europe, and companies can buy or have to buy these when they have to for their emissions. By 2050, of course, these emission rights are going to reduce to zero. So the longer or the further we go into the future, the less emission rights will be available and the higher the price. So when it comes to the why statement, or why is this presentation important? Well, firstly, you have to. Europe, if you're a European country or company, then the European Union actually tells you to do that. Now, secondly, on top of that, you see at the bottom of the screen a trend of the actual CO2 price in that ETS system. And you see that not only the oil, the gas, the electricity went up, or the price of raw materials, also the price of CO2 went up drastically in the last year. So a year ago, it's probably a bit too small for you to see, but a year ago it was around 40 euros a ton of CO2. Nowadays, we are at 85 euros a ton. And so that is a bit of a game changer, because whereas before we saw a lot of projects that focused on more throughput, nowadays we actually also see more projects that have the same throughput, but that just want to use less electricity, a more optimized process, or even less emissions. So it's a bit of a shift there. So the why statement is, well, because you have to if you're a European country, but also because it's economical viable at this point in time. So Edwin already mentioned, so it's a bit of a diverse audience today, but most of you are probably part of the process industry, such as petrochemicals, refining, and chemicals. These are among the top emitters of emissions. And each of these companies will have to comply. So they are responsible for meeting all the environment legislations, and that includes accurate emission reporting and reductions. The European has put a lot of measures in place. It's very detailed, but I'll try to give you a bit of an overview there. So that brings us to the first use case, so measuring your emissions. And this use case is really all about reporting of your emissions. As said, the European Union has put in place a lot of measures. So there are European emission standards that really tell you these are guidelines for analyzing and reporting your emissions. They tell you what to measure, so greenhouse gases, which greenhouse gases, which ozone precursors. They tell you how to measure it. So for each of these pollutants, they actually have approved technologies that you can use, approved meters that you can use. So it really goes into a lot of detail on what to measure, how to measure it, and how to report it. And that I want to demonstrate a bit on my next slide. So on the right here, you see that the landscape was so complex that the European Union actually created a quick guide. And this is a very specific quick guide for operators with stationary installation on how to do emission reporting. Now, this quick guide itself is, I think, around 12 pages, and it gives a quick and very good overview of where you have to be. So it's full of, well, you see all those documents listed there. So it's full of references to those documents where then more information is available. Just to show there's a vast amount of information there. What you see on the left is the document. So the quick guide actually starts with this plan that tells you as a company what you have to do each year and what time of year you have to do that. Next to the operator, you can also see that there's many stakeholders in place, so competent authority, verifiers, and a national accreditation body. Just to say, there's a lot of information there and it's very detailed. Now, I'm not gonna give, let's say, a quick reference to the quick reference guide. No, I'm just gonna start and say from a very high level point of view, everything stated in the documents actually come back to the same, being the biggest emissions should be monitored most accurately. How you monitor them, using measurements and analyzers or using a calculation-based approach. The European Union leaves that a bit in the middle. As long as the accuracy is assured, it doesn't really matter if it's the accuracy of measurements or if it's accuracy of calculations. And that's also what you see at the, the classification of your process is very important, because this classification leads to what they call tier levels. And those tier levels, that's actually that accuracy that I was talking about. And the table at the bottom of the screen, you see the different tier levels. So it goes from 1 to 4, and you see which accuracy actually corresponds to that. For the highest tier, you can see that the accuracy or the uncertainty has to be less than 1.5%. Now, how does this classification work? The classification is really based on, firstly, the installation itself. So it means how many emissions are produced by average over the year. So that gives you a bit the idea, that puts you in a certain bucket. Afterwards, it focuses on the different source streams or emission streams that is there. Now, source streams, emission streams, they're basically the same thing, but they use a different nomenclature based on if it's a calculation-based method or a measurement-based method. Now, these streams is actually all the fuel or material that goes into your installation or comes out of your installation that has a direct effect on your emissions. So that's the definition of these source streams or emission streams. The same there, they get categorized. So if it's a not so important stream, it will be de minimis. And so the tier that comes with that will be much lower. If it's a very big stream with a lot of emissions, it will be a major one and your accuracy increases. Now, going forward, I'll show you both an example of this measurement-based and this calculation-based approach for emission monitoring. And I'm going to start with a measurement-based, so what in the nomenclature they name continuous emission monitoring system. So it's really an emission, it's really geared towards emission monitoring based on the use of analyzers. And in this example, I'll talk you through a project that we are currently running, really focusing on monthly emission reporting. Now, you might have noticed that from the slide from the European Union, they actually only talked about yearly emission submissions. So on top of the requirements of the EU, you actually also have other requirements, for example, coming from the government. And so this monthly emission report, in this case, is really a requirement that comes from the government. And if we look a bit at the diagram at the bottom right, you would think that this is actually the most simple use case, because, well, in our factory at the bottom right, we have 3 chimneys. We have analyzers that are put on top of these chimneys. We have the measurements, and these measurements we have to report. So it feels simple, especially because the EU actually says how to do it, which equipment to use, and how to report it. Now, if we look into more detailed into these requirements, you see that it's actually a bit more complex. So firstly, you need to use high-frequency data from these analyzers. In this project, that means data sample every 10 seconds. Okay, that's not really a concern. Next requirement, an external agency needs to calibrate and check your analyzer. This calibration actually happens in a certain interval or bandwidth. And so you have to ensure that you always produce within this interval or bandwidth. If not, you will have to call the external agency again and calibrate over the new measure that you're actually now producing. So it means that it becomes already a bit more complex because this monthly reporting already becomes a more continuous process, because this check, are you within your calibration interval, is something you will have to do with every data point that comes in. Because I think that the measure was 2%. If in a day you have 2% of values outside of this, you will actually get penalized for that. Now, next up, we will have to convert this into hourly, daily, monthly, and yearly totals. Next thing you see is that if your installation is actually ramping up or ramping down, you do not have to include the emissions of that period in your reporting. So you feel that the more requirements become clear, the more this is actually a real-time monitoring exercise that we are doing. So even for monthly emission reports, you actually have to keep track of this in real time, because when you generate a report at the end of the month, you obviously do not want to see, oh, we missed something, we're way off, and we now have to pay a fine for that. So monthly reporting is actually a very real-time process. And that's actually where our first real-life example comes into. I'm not going to show you an emission report as such. I'm going to show you the governance that we need to put in place to actually ensure that at any point in time, we can generate a report which is not in violation of the rules. And on top of the screen, you see the emission compliance. So that are these hourly, daily, monthly, and yearly values that the EU tells you to calibrate. You see the different pollutants and you see the different chimneys there. At the bottom of the screen, we see the calibration status. So we see for all these analyzers if the agency, the external agency, has already done its calibration, and if they have already provided their tweaking factors that we have to apply. Now, before the Q&A gets flooded by question, I'm very aware that CO2 is not part of this screenshot. And that is because in this project, the company actually chose to use a calculation-based approach for CO2, but to use a measurement-based approach for these pollutants. So a company is free for each source stream to decide if they want to go for one or the other. All right, so that brings me to the calculation-based approaches. And so as mentioned in the project that we run, CO2 was one of the main things here. So dependent on your process, different calculation methods can be applied or are allowed to be applied. I'm going to start with the most simple one. So the example of CO2, there it's what we call a fossil fuel combustion model. So there's a direct relationship between the inputs of your fuel gas and the emissions that come out of it. And at the bottom of the screen, you see the formula that actually describes that. So you have your emissions, which are calculated by your fuel quantity, the net caloric value of your fuel, the emission factor, and the oxidation factor. Now, these are a lot of factors, and I want to go back a bit to that tier that I discussed before. So the bigger the source stream of, and typically fossil fuels are, of course, a big source stream. The bigger the source stream, the bigger the tier, and so the more precise all these values have to be. If it's a very small process, you can just use default values for all these calculation factors. If it's a high tier, then you really have to go and conduct laboratory analysis on top of it. Now, just to show or just to explain you this principle, because I'm not going to show you any new screens, because at the end, the governance around this will be the same. You can make the same dashboards around governance using these calculation-based approaches than I showed you for the measurements. But I wanted to show you this, calculation method because it actually ties to my next subject. And so my next subject is, how do we actually identify these main contributors in my process? So before I start about real-time emission monitoring on equipment, I want to take one step back and say that real-time monitoring of equipment, what we see in the field is that it's a very well-established process. So we see a lot of companies that have taken very far steps to actually do this operational monitoring. With this operational monitoring, we mean that, well, you want to determine the status of your equipment. So you want to know, is it running? Is it stopped? In further cases, you want to know, is it ramping up? Is it ramping down, etc. And on top of that, you also want to know where in your operating window are you operating? So are you operating close to your design limits or not? So we see that this process is very well established. And going from real-time monitoring to real-time emission monitoring is a very small step, because you can already feel that the status of your equipment, is it running or if it's not running, is also directly related to your real-time emissions. You can already feel that if your machine is using more fuel gas or has a higher power, you can already feel that also there your emissions will be higher. And so the same calculation concept that I explained just before on the source streams, you can actually also apply that to your equipments, and that helps you to identify the main contributors of emissions in your process. Now, if you add a target into the mixture where you can benchmark against, you get a nice system where things are trackable in time and where you can extrapolate that towards the future. And that's my next real-time example. So in this project, as you can see, we have applied the real-time emission monitoring on the equipment level, and then we just summed it up over all the hierarchy, over the entire hierarchy. So what you can see all the way on the left, you have your total CO2, which is then divided over rotating machines and flares. Rotating machines is divided further. So in once, and this is also in real time. Let me clarify that as well. So with one look, you get to see, okay, my biggest emission contributor at this moment is turbine D. What you see on the right is when you add targets into the mixture on these equipments, then you can very quickly see, okay, which machines are running according to their target, which machines are running above their target. And if you go one level deeper, if we actually look at this at the equipment level, you get a very nice overview. So at the top left, you see the equipment we're now looking at is turbine B. At the moment, it's online, and the current status of its emission is it's above target, because you see the current estimation there and you see the target. Okay, we're above. When you look at the window on the top right, you see that if you extrapolate this over time, you actually get a quite good feeling of, okay, how are we doing compared to these targets? And what strikes immediately is those two very big spikes. So by implementing this real-time emission monitoring, it becomes very obvious. Like when you see those two big spikes, everyone who sees this will ask the question, oh, but what has happened there? You actually direct the attention there, and you can start discussions with the people that are involved. Okay, so two more screens to discuss. So the bottom right is the same graph, but a cumulative of your CO2 emissions against your target. And by extrapolating that towards the end of the year, you actually see, okay, if I continue the way I have been producing this year so far, will I reach my end of year target or not? At the right bottom, you see another graph where we actually show, okay, this CO2 emission, how is that correlated to the energy produced? So you get a bit of a feeling of the efficiency, how you are operating at the moment. All right. So to summarize this a bit, these real-time emission monitoring, as said, so it's a soft sensor approach. So we use calculations on real-time measurements, either fuel gas or related parameters such as the power that actually give you a good indication of the emission. So there's a direct relation between those parameters and the emissions. Now, if you say, okay, but I don't have those measurements available, well, consider maybe putting IoT sensors on key measurements that are missing. Nowadays, with the whole, the whole, I should say, evolution of IoT sensors, getting measurements became way less expensive. So it's always a good idea. Now, certainly, if you have not yet started with your real-time monitoring, then if you make the business case for implementing real-time monitoring or real-time emission monitoring, well, know that you're also unlocking further use cases. You're not just implementing this, of course, to monitor your emissions, but know that also there you will have events, you will have certain targets and limits that you define. So you actually contextualize your data, you enrich the data that you have, which is then used, of course, by your analytics and all your layers on top of that. So know that this is the basis for other use cases. And lastly, well, you're not constrained to only choose one or the other. If you have measurements and calculations available, well, then you can even further optimize this and you can start doing, or you can start fine-tuning the emissions, the emission estimates that you have by comparing them with the measurements that you have at your analyzer. So that's a typical back allocation issue. Okay, so that sums up a bit measuring your emissions, sums up a bit where are they actually coming from. And now the last part, we'll talk a bit about how can we actually reduce them. And to start, I'd like to show these different best practices or these different means to actually reduce your emissions. And so I've put 5 of these best practices here, and I'd like to go over them one by one. So the first one is housekeeping, and housekeeping is the same as if you're at home and you're not in a specific room, then you turn off the electricity. So just by creating awareness, you are able to reduce the energy consumption and you are able to reduce the emissions associated to that. Second step, control systems. So that's the typical APC projects. So that's the typical unit optimization that we talk about. It's a bit more effort. You don't do it just by understanding. There might be some more projects involved, but typically housekeeping and control systems, they still really focus on existing infrastructure. Then the next step, simple modifications. Then you already start thinking about, okay, maybe we should, well, with the existing infrastructure, we're probably not going to get, or we're not going to get our emissions all the way to 0. So these simple modifications is, for example, at the moment you have a compressor which is fueled by fuel gas. Maybe at some point you'll remove it for an electrical compressor. Fourth step is the process integration. Process integration is on your entire installation. So where APC and control systems is really on a unit basis, for process integration, you look at it over the entire, over your entire installation. Lastly, you have the alternative process, and an alternative process is really doing things completely different. Maybe the things you want to apply there haven't even been invented yet. So it's really getting a whole new, fresh way of working for the process. And an example of that is, for example, in Oman, there's now a fully green ammonia plant. So they only use wind and solar power to power that ammonia plant. And so we as IPCOS are very happy to actually provide the APC services for that project. So that's a bit the 5 best practices. And I'll now show you some example of each of these best practices. And I'll start with the housekeeping. So housekeeping, well, we already discussed quite a bit of housekeeping up until now. For example, if you remember in identifying the main contributors, in that screen where we showed the emission estimates over time, we had those two very big spikes. So that's actually already a form of housekeeping. So you get emissions embedded in your process, and when you see things like that, they will be discussed and questions will be raised. And so in the example that we showed, it was actually the venting of steam, which is a very common used process, which seems very harmless, but of course, the steam contains heat, and by venting this heat, you also have a negative effect on your emissions. Other emissions or other housekeeping that we already discussed is our emission. Your real-time emission story was really around rotating machines and combustion of fuel. So all of these things were already examples of housekeeping. But I want to also add one more example there, and that is the heat recovery maximization by fouling monitoring. And here there's a bit of a more indirect link between the process and your emissions, but you can already feel that there is a link, of course, because the higher the heat recovery maximization, well, if you can use the heat somewhere else in your process, the less, of course, you have to actually heat up other parts of your process. And so the less fuel gas and the less emissions you will have to use. Now, when we look to fouling of your heat exchange, so yeah, it's a fouling monitoring example. Now, what is fouling? Fouling is, in a heat exchanger, actually a measure of, let's say, sediments that stay behind from the process flow on your heat exchanger. And so these sediments, actually, the result of that is that the heat exchanger efficiency goes down. And at the bottom of the screen, you see this 3-month data that we have. And in blue there, you see the fouling over time. What you see is that the fouling actually increases. So your efficiency goes down up until the red line. The red line is actually your maintenance. So the fouling drops after your maintenance. It increases again, it drops, etc. Now, typically, this fouling is monitored, let's say, once every month to once every 6 months. What this project was about was to actually perform this fouling monitoring in an online fashion. So we're not talking about that 10-second interval that we were talking about before. No, that's a bit overkill. We're actually talking here about daily estimations. Well, firstly, it's not required to go to that low of a granularity, but secondly, also for this, we actually use heat exchanger physical models, so they are way heavier to compute, of course. So we can't do this on a very high frequency basis. That's why daily value is, of course, already a lot better than once every month or once every 6 months. And what is typical advantages of this fouling monitoring is, well, it helps your understanding. And also what you see in the bottom graph is that the understanding that it gained with this fouling monitoring is actually a relation between the flow of your process flow through your heat exchanger and the fouling that is associated to it. So the heat exchanger that you see there at the bottom, the data is actually from a heat exchanger that was used in parallel with another one. And in the third period, so a bit in the middle of your screen, they actually started playing around with this. So they started to say, okay, what if we turn off one of these heat exchanger, which increases, of course, the flow through the only remaining heat exchanger. And they saw with this higher flow, they actually found that the fouling was not as bad. And that's also what you see in the complete right of the screen. The fouling remained pretty much constant as long as the flow was higher than what they did before. Another typical example of a benefit of this fouling monitoring is your maintenance planning, because you get a very good view every day on how well or how much the fouling of a heat exchanger is, taking into account the importance of that heat exchanger and the impact of it, you can actually very easily or more easily create your maintenance plan. Now, these benefits are, like I said, maybe quite indirectly related to emissions, but in a second phase of the project, they actually went one step further. In that phase of the project, they actually had a research project in which they tried to correlate the composition of your process flow with the measure or how much the fouling actually increased because of it. Now, by doing that and by integrating it with their production plan, they actually obtained this kind of predictive fouling. And this measure, they actually translated to a lower inlet temperature of your furnace. This lower inlet temperature, they then related to more fuel gas that was needed to achieve the same temperature, and that they related to the emissions. So by implementing that next step, there's actually a more clear correlation between your emissions and this heat recovery maximization. All right, so that were two examples of housekeeping. Now, next up is the control systems. And a typical control system problem or a typical APC problem, you will always have constraints that you need to meet or maximize, and you will have certain handlers that you have to actually meet those constraints. That's the typical start of an APC project. Now, taking those constraints and handlers into account, you will try to improve the equipment efficiency. In our case, when it comes to emissions, that can be reducing fuel gas consumption, it can be reducing steam consumption, can even be stabilizing the operation as such. Another thing, well, to not completely lose track of that heat recovery maximization, well, that's also one of a part of an APC project sometimes. Okay. Now, to actually demonstrate this a bit more in detail, I'll have to explain the brown purifier ammonia process. Before everyone starts logging out, I assure you I won't go into too much detail on this process, but I will try to explain a bit the basis that I need for the rest of my explanation. So in the middle of the screen in green, you actually see, or at least for my explanation, the start of the process, you have a primary reformer where you use fuel gas to actually heat this up. Afterwards, you have a secondary reformer where your chemical reaction is already at full speed, and so temperatures there are around 1200 degrees, so you don't really need to heat it up. Well, you don't need to heat it up anymore. The idea of these reformers is that methane goes in, and by the heat, you want to get hydrogen H2, you want to get hydrogen out. Now, after these reformers, the next step is to merge them up with air. So air is rich on nitrogen. And, well, you have nitrogen, you have hydrogen. So that's the basis for your ammonia or NH3. Now, this is a very slow reaction. So when you merge the air and the hydrogen, it's not an instant reaction. That's why in the bottom right, in blue, you actually have what they call the loop. So a loop is a very big, so where the air and the nitrogen stays together for a while. I think the conversion is typically around 30%. So yeah, typically it takes around 3 rotations before actually the ammonia is formed. So primary reformer with fuel gas, secondary reformer does not require fuel gas. You merge the hydrogen that comes out with it with air, and you put it in a big loop to actually make it react. That's a bit the summary of, well, this particular implementation of this ammonia process. Now, if we then look to my real-life example, you see on the left in red, you see APC was not turned on. In the right, you see the APC was turned on. Let me start at the bottom of your screen with the air-to-gas ratio. So the air-to-gas ratio, as you can already feel, in the ideal situation would be, let's say, a 1:3 ratio. NH3, so a 1:3 ratio. But of course, the hydrogen that comes out of your reformers is not always the same. So for an operator, it's not always easy to control that, especially not because there's that very big loop afterwards. So if you change that air to gas ratio now, it will take maybe 6 hours before you see the effect of it within that big loop. So for an operator to do that manually, that's very difficult to control. That's what you see on the left. Whereas on the right, with an APC project or with a model predictive control, you can much more finely regulate that. Now, on top, you see that methane slip. So that's actually, in this case, I told you there are constraints and there are handlers. So this methane slip was actually the constraint in this process. So the methane slip is the amount of methane that goes to the secondary reformer without being changed into hydrogen. What you can even see is a bit like after a few weeks of using the APC, they actually started to trust the system and they increased their constraint even a bit. Whereas before, without the APC, you see that it's a bit all over the place. It's much more difficult to maintain that constraint. Now, that brings me to the middle of the screen. This is the temperature of the primary reformer. And you see that because of the APC, you can go, well, you can not only make the furnace more efficient, which is not shown in this graph, but you can also make this reaction happen on a lower temperature. So that's what you see. Before APC, there was a much higher temperature than after the APC project. Now, that brings us to the easy part of the explanation. So less fuel gas that is required to have for the lower temperature, of course. So it means less emissions. So that's an example of an APC project to reduce your emissions. Now, as I already said, housekeeping and control system is really all about existing infrastructure and all about, let's say, high frequency and online manner. The remaining 3 is more about changing infrastructure and about offline analysis. Like, how do you judge the impact of changing a fuel gas-driven compressor with an electric compressor? And offline and design is not always correlated with digitalization. So people always think of that online component, that high-frequency data. But there is also a relation there, and that's I'm going to bundle those next 3 best practices into one, and I'll discuss them as a whole. So the statement here is that the more a company has digitalized and automated its processes, the easier it will be to adapt. So as I said, how will you know what the impact is on your process if you have nothing in place? Well, it's not that easy to give that example. Then how do you know if you are talking about redesign of your factory, how do you know how to redesign it? And that's actually where at the bottom left you see that I introduced the digital twin concept. So a digital twin is, let's say, a digital copy of your equipment. So digital twin, typically you have different pieces of information. So you have your design models from your pre-production phase. You have your technical drawings of any changes that are done afterwards. You have your process data of your production. And all of this combined, of course, give you a very rich understanding of your process. And all of this together will help you to judge on impact, to judge on the redesign. So even in this offline environment, digitalization plays an important role. Now, that brings me to the conclusion of my presentation. So I would like to say that digitalization alone will not get your emissions to 0, but it is an integral part of it. And I hope that my real-life examples over those different use cases actually demonstrate the nice interplay between digitalization and net zero. All right, so that's it from my end. So I now open the floor for questions.
Thanks, Martin. That was very insightful. As Martin said, we have time to answer questions you may have. And as I mentioned in the introduction, you can post your questions through the Q&A window that's on the left side of your screen. Marta, I'll start with some of the questions that came in during the session. First question, in your story around identifying the main sources, you only talk about CO2, where in the introduction you talk about greenhouse gases, different greenhouse gases. Do you apply the same real-time emission monitoring principle on other greenhouse gases?
Yeah, so I think indeed the same principle can be applied as long as I would say the greenhouse gas in mines has, I would say, the same characteristics. But let's take, for example, methane as an example. So I think the same mechanism definitely applies to methane, but the question then becomes also a bit, well, where in your process is your methane escaping? Is it part of your combustion as CO2, or is it more, well, methane is a typical example that maybe, well, it cannot, maybe it's already escaped before it actually reaches that end state of where it's being measured. So I would say, yes, definitely the same principles could be applied to the same emissions or the same different greenhouse gases. But of course, the same rule should apply there as well. If it escapes somewhere else in your process, of course, then yeah, you will have to have a different mechanism for it.
Excellent, thank you. Next question is, you talked about the quantification of emissions and different methods that can be used for this. It feels strange there is no difference between measurement-based or calculation-based. Does the EU stipulate a preferred way?
Right. I would say that there are some exceptions, but most of, well, in most cases, the EU does not stipulate an actual preference. So if I'm not mistaken, for example, carbon capture. So if you are capturing and storing carbon, that is one of the exceptions that you always have to measure. I think another one was N2O. So these really are things that are very detailed described as you have to use a measurement approach for those. At the other side, I think there's also some examples for things that always have to be calculation-based. I think one of them is, for example, the emission of biomass. So if your fuel is coming from biomass, you do not have to allocate that. But of course, at the end of your process where you measure your emissions, for example, well, the biomass emissions are, of course, also included in that. And so then there, you would actually use a calculation-based approach to estimate these biomass emissions, to then deduct them from what you measure at the end.
Excellent, thank you. Next question is actually close to my heart. Do you include reducing emissions as a control objective in your APC applications? Do you want to answer that, or do you want me to elaborate on that?
Since you said it's very close to your heart, so I'll give you the honor of replying this one.
Thank you. Thank you. Yeah, the answer is we do, but typically only implicitly. The energy minimization is an explicit objective of every APC application that we build. And by minimizing energy consumption, you implicitly minimize the emissions. To be honest, technically, there's really nothing against including an emissions parameter measured or calculated in the APC application. But the horizon over which the emissions are typically measured and reported is typically a lot longer than the APC control horizon. So we normally don't include those parameters explicitly as CVs in the APC. All right.
I would not have explained it that well, so good thing we passed it on.
All right. That is it. We have then come to the end of this webinar. I'd like to thank Maarten for your insightful presentation, and like to thank all the attendees for your time. And we look forward to seeing you on one of our future webinars. Thank you very much and have a great day.
Thanks, everyone.